topic that is very interesting to me because it has an application towards communication systems, which is one of the things that I've throughout my career been very much interested in. So I'd like to talk to you a little bit in the short time we have about the state of the art of quantum communications. And if you're not aware of what quantum communications is it's using this property of quantum entanglement to exchange information from a transmitter to a receiver. And the way it works is they use a fiber optic cable to transmit photons that have been specially prepared. And on the receiving end, they are able to extract information that cannot be determined without observing the cable. But if you observe the cable, you lose the information. And so it's a way of securely transmitting information from one station to another. So the state of the art of quantum communications is to use that channel to transmit the keys for an encrypted link. So you can get a secure end-to-end communication through by transmitting the keys securely. And so, of course, the government and financial sectors are very interested in this technology, and this represents the state of the art. This is a system that is running at BDN Technologies in Boston. It's a DARPA quantum network testbed, and this was published in 2007. Now, one could say, well, what if you just break the link? Haven't you lost the key? And so what the folks at this research did is they set up an elaborate system of network relays to maintain these links so that if you lost a link, you could still route the key and maintain your secure encryption channel. So you'd have a fiber optic cable here, a separate fiber optic here, a separate fiber optic here, and lots of computers along the way. This is in 2009, work was done in Vienna on a quantum key distribution network. And there's a piece of equipment. This is real hardware that's being used today. And what you see here is over the course of several hours, your quantum bit error rate, or the bit error rate seen in the quantum channel, is about 3%. So we're not talking about very good rates, but and so what they have been able to observe is just a little over 2 kilobits per second, which is just about enough to transmit one key every second. So if you maintain, so you can effectively create a secure communication in which the key changes every second or so. And so it's practically unbreakable from that perspective. That's the state of the art. Some work done at ORNL in 2004 focused on using quantum entanglement for interferometry and measurement. So what they did is they set up this apparatus to create entangled photon pairs and then be able to measure them. And the idea here is that you have a laser, say a high energy laser such as a blue or a purple laser, and it goes into a non-linear optic crystal. And when that happens, you get a parametric down conversion, where the high energy laser beam turns into pairs of lower or longer wavelength beams. And what you get is you get red, for the sake of example, depending on the crystal you use, a red and a blue beam, or a red and a green beam. Now you don't know which one it is. Okay, you might get a red, you might get a green. Okay, and what happens is they come out in pairs. And if the properties are right, and the way the professor explained it to me was that the emission of the photon, of the green or the red photon, occurs when you have two valence state changes within one revolution of the electron around its orbit. That is what creates the entanglement. So you get a red and a green, right? Okay. Now, what they did is they mixed it all back together, so effectively you shuffled the laser beam, and then they send it through an elaborate system of detectors. And what they did is they put a beam splitter in line with one of the beams, and they basically sent the beam into a specimen where they were able to observe the height map, or effectively the surface of the specimen.
You got 5 minutes.
And what they found was that there was a correlation, and I apologize, this is just a drawing, that's how it is in the published paper. What they found is that there's a correlation between the depth position and the coincidence count rate at the different detectors. So what they effectively did was they measured something, they measured a physical process at a different place in space, but at the same time. Okay. And that's just a picture of their apparatus that they formed. Okay. Now, this is a really exciting experiment that was conducted, where was this? This was in Geneva in 2008. And what they sought to do was to try to eliminate the possibility that the measurement between two places had any kind of classical communication. So here you have a similar system for creating entangled photons. You send one set down a fiber optic link to two different places separated by a sufficient amount of distance between them. And then they set up an elaborate system of detecting a single photon, which would move a piezoelectric mass. Okay? And the postulate was that the collapse of the electron, the measurement of the electron, doesn't finish until a mass, a macroscopic quantity, has moved. Right? But everyone agreed that, okay, if you did that, then clearly the wave function has been collapsed and you have completed your measurement. And what they did is they set it up so that the detection, the time of detection, took 7.1 microseconds. Right? And what they did is they adjusted the temperature of the interferometer, right, by degrees from 21 to 40. And so what they were able to do was observe temperature changes at this interferometer occur at this measurement point. Right? So they effectively transmitted information from this station to this station over the course of time. And of course, because they did that, the time separation in classical light speed is 60 microseconds here with an 18-kilometer separation. So they effectively proved that they could transmit information from one station to another faster than light. And this is a graph of their experiment with error bars to show you over the course of time, as they varied the temperature, what they were able to observe at the Justin station. Okay, so why is this interesting? What can we do with this? I propose that what we can do is set up. I apologize for the colors didn't come out quite right. But effectively, we can set up a relay station, but not in the case that we would if we were to want to communicate between the Earth and Jupiter, we would set up a station where we generate the entangled photon beam somewhere equidistant from the two stations. And here is where we send this beam out this way and this beam out this way. Now remember, from the experiment before, you send out you begin at your source with a beam, and you have a classical travel, so that you have to send the beam out to your 2 points. But then you perform effectively a transmit operation by collapsing the wave or observing the photon. Say you observe red here at A. Well, at the time you observe red, you force green at B. Right? And so if you can adjust the times at which you observe and at the two stations, you can actually know that if all B does is listen, and it has a slightly different time delay from A, then if A collapses red, B will observe green. Now, if A can contrive to collapse green instead of red, then B will see red instead of green. and vice versa. And so you can transmit information, and that's how quantum information is transmitted, right? From one station to another, and you can effectively bypass the time that it takes. So, yeah, this doesn't show. So the idea is yes, it takes 50 minutes for the beam to go from the photon source to the station here, and it takes 50 minutes from here. But to communicate from this station to this station is instantaneous, and it doesn't matter if we do that on Earth, across the solar system, across the galaxy. If we can deliver that laser beam, if we can deliver that light to the far end station and collapse it in an appropriate way, we can communicate. And so I think the next talk is about communicating with lasers, which I think is extremely apropos because it can allow us to realistically communicate with our spacecraft at extrasolar distances.
We have time for questions for the dual speakers here, so we can start out.
So, if I understand you correctly, you figured out another way to skin Schrodinger's cat.
It's possible.
The fact that the initial tangled photons have to travel like you said, you have 50 minutes in the diagram.
Okay.
When you finally observe them, you can't communicate between the two destination points. You can only know what that other destination knows. Because when you observe the photon, it will break the entanglement, and you only know what it was.
That's right.
But you can't force it to be what you want it to be to send any kind of binary signal.
You can. And this is how you would do it. You would have a mirror at which you could deflect, selectively deflect the red or the green, right? So let's say you have a common beam, right, which has both red and green mixed in, right? But you have a detector, and you set your mirror to basically deflect just the red. The green, if the beam becomes green, it won't go into the detector, it'll keep on going, and it doesn't get absorbed. So by selectively absorbing the color of the photon you want, you can ensure that you're only absorbing red during this phase, or at this moment in time, you're only absorbing the red photon, and you're letting the green go.
But it doesn't matter whether you absorb it or not, it's either going to be red or green. It's not the observation that makes
It is the observation.
So it's when the wave function collapses.
Yes. Which, when it will collapse when you observe it. And if you force the observation of the red, for example.
I think there's a misnomer in collapse, in the difference between observation and collapsing. When a plant absorbs a photon through photosynthesis, that's collapsing a wave function.
Okay.
And it's not that human act of observing it with your eye.
Yes.
It's the transmission of energy from one form to the other through any kind of form of interaction.
Yes.
So it doesn't matter how you observe it, it is what it is.
Okay.
And so there's no way you can force it to be what you want it to be. All you can know is about its initial state.
Well then, how do they transmit quantum key pairs then?
Oh, well, that works, except it's not really instantaneous communication because, like you said, they have to start off with the initial position of these photons, send them out, and then you know what they're going to be, but it's not actually instantaneous communication because they have to travel their given speed of light.
Oh yes, but you've already paid that. You paid that time by waiting the 50 minutes.
Right, so it's not really instantaneous communication.
It isn't, but here's the thing.
It's instantaneous knowledge of where something is somewhere else, but it's not a way of instantly communicating.
So this is a perfect reason to fund additional kinds of experiments with the intent to determine if information could be transmitted.
Sure, it's worth a study, absolutely. Yes,
If you're,
I want to say something about that too. But I had exactly the same objection you have. Basically, the beam turning, you've got a degeneracy, you don't know what it is. And you remove the degeneracy by making measurements. Only then have you crossed the wave.
correct.
And that's the Copenhagen on mechanical beam. There seems to be a movement that says you can sort of sample the photon and know what it is you have to ask. If that's valid, and that seems to be what people are saying. If that's valid, you don't collapse the wave function unless you want to. You don't truly read it out. and it's that magic that's there. I don't, I'm not so comfortable. There's no different.
Don't forget the experiment at Geneva, right? This is a plot measured at Jussie of the temperature at stagnant. A completely separate process that Jussie had absolutely no knowledge of, and certainly the generation of the photons at Geneva. So that's a seminal paper that I think really sets the experimental basis for this optimism.
Well, the chair is going to request that the debate be deferred to
Yes,
offline so we can get on with our next presentation. So thank you very much.